In our previous video, we have explored the situation when we mix a strong acid with a strong base. In that specific case, we had hydrochloric acid that was mixed with sodium hydroxide, but because both are strong, so you can just consider how hydronium reacts with hydroxide to give water. So the pH was determined by how much of one or the other was left after reacting. Initially, because we only have HCl, and let's remember this was, you had the Erlenmeyer with the HCl down here at 0.1 molar, you had 10 milliliters, and you have the burette here in which you're adding the sodium hydroxide 0.1 molar. Initially, if the concentration is 0.1 molar, the pH is 1, so you start something like this. And you just need to build the ice table to figure out how much of the hydronium is left to calculate the pH, but notice that initially the pH barely changes until you add as much sodium hydroxide as hydrochloric acid there was. We did that in moles. It's very convenient to do it in moles because concentration will change because you're changing the volume, so it's better if you just do it first in moles. At the point when you have added as much OH than hydronium, this is called the equivalence point. The equivalence point when you have strong acids and strong bases is always 7 because the product is just pure water. This will change when we have weak acids and weak bases, but when you have strong acids and strong bases, the so-called equivalence point, that is when you have added the stoichiometric amounts of both reactants, the pH will be 7. Notice that after the equivalence point you will have what is called an excess of hydroxide, so that pure hydroxide will have very high pH, or if you will, very low POHs, high concentration of OH negative. So expect this kind of shape, having this pH equals 7 at the equivalence point when you mix strong acids with strong bases. So let's practice a little bit if we can apply this simple exercise to other situations. For example, in this case, it's asking us to draw two titration curves. In each case, okay, you have to identify the initial pH, the volume at the equivalence point, or if you will, sometimes the equivalence point is called neutralization point, and the pH afterwards, after the titration, after the equivalence point. In this first case, you have 50 milliliters of 0.1 molar of nitric acid being titrated by sodium hydroxide. Well, if we draw the curve initially, notice that it's 0.1 molar of a strong acid, the negative log of 0.1 is 1, so initially the pH is going to be, pH is going to be 1. Okay, so you start at 1. Now, I have 15 milliliters 0.1 molar, and I'm titrating with 0.5 molar. The question is, how much sodium hydroxide contains as many moles of hydroxide than nitric acid or hydronium? Notice, and this is something that you may want to do, but if you have 50 milliliters, 10 to the 3 milliliters is 0.1 molar, 0.1 moles. This is 0.005. If you want to know how many milliliters there are, so if you want to know, how many milliliters it takes to have this many moles of hydroxide, notice that if you do this, this is moles, I apologize, this is moles, so in 0.5 moles in 10 to the 3 milliliters, this will give you 10 milliliters of sodium hydroxide, 0.5 molar, contain the same number of moles of hydronium of 50 milliliters. But I'm saying this because it will be, the equivalence point will be when you have added 10 milliliters of sodium hydroxide. Okay, at this point you will have the equivalence point. And it's important to understand how much sodium hydroxide do you need to add to neutralize the acid in 50 milliliters in 1 molar of nitric acid. It makes sense because the concentration of the base is 5 times, so you should have 1/5 of the initial volume of 50 milliliters. 1/5 of 50 is 10 milliliters. Okay? And because it's 5 molar, you will have a curve something like this. And where is it going to go? It's going to go a little bit above 13, because if it were 13, it would mean that the pOH is 1, or it tends to go to 0.1. As you add more and more sodium hydroxide, this should tend to 0.5. So it should be a little bit above 13. Okay? This may look new. I would advise you to go slowly, but unfortunately we cannot take as much time in videos, but we'll definitely practice in the class. But the process is always very much the same. Notice that nitric acid and sodium hydroxide are both strong, so the equivalence point is always at 7. Initially you only have acid, so that will be your initial pH. At the end you'll have mostly only hydroxide, so that will determine your pH. Notice in this case it's a little different. We have base. So we have in our Erlenmeyer, we have base 0.1 molar. That means that our initial pH will be 13. Hopefully I'm not going too fast. That is that the pOH for a strong base is 1, so 14 minus 1, the pH is 13. Now, notice that potassium hydroxide and perchloric acid are both 0.1 molar. Therefore, if I have 20 milliliters of 0.1 molar potassium hydroxide, I need to add 20 milliliters to neutralize completely the base. So if this is 20, it'll be at 20 that I have reached the equivalence point. Okay? So expect something like this, and this will tend to pure 0.1 molar. Perchloric acid should be around 1. Again, I'm going very fast, but notice that if you can catch all the approximations, the pH of a 0.1 molar solution of a strong acid is 1. The pH of a 0.1 molar solution of a strong base is 13, because it's 14 minus 1. Again, these are some tricks that it's good that you can do fast, because when we deal with more complicated mixtures, these kind of skills will be required. We'll definitely practice more, but at least these are the tricks of the trade.